Welcome everyone. In this session today, I am going to talk about the theoretical foundations of distributed computing. In the last sessions, we started with the topic of distributed systems, and we said that a set of computers interconnected together over a LAN or a WAN network looks like a single virtual image, and this single virtual image can be accessed from anywhere and any location. But when we talk about single distributed system, there are various issues in the system in designing it, which we had covered last time. We talked about scalability, we talked about various other aspects in terms of reliability, replication, transparency, etc. Then we also talked about two different protocols of distributed systems, that is VMTP and FLIP. And then today we will now look at theoretical foundations. What exactly does the word theoretical foundation mean? In a particular system, when we talk about the distributed system and the clock environment around it with a shared memory or no shared memory, this single entire system now looks like a single virtual image where any user can access it from any different location. So to look at in terms of theory, what are the different algorithms we can have, how we can design them. In this particular session today, I shall be discussing various parts of aspects of a distributed system, like what are the limitations in a distributed system. We'll look at how to manage physical clocks in a distributed system. We will also look at Lamport's logical clock. We will look at vector clocks. Then we'll see what is the global state of a distributed system, and it will be followed by the concept of termination detection. Now basically a distributed system is a system which is also used along with a distributed database. When we use it, the distributed database is spread across different locations, but it can be accessed from any location, and we would like to get the information from any location in instant of time. There should be no delay. So how do we manage this? How do we ensure that transactions triggered from one particular location can be accessed and can be committed in another location? So for this particular idea, we are going to look at theoretical foundations of distributed systems. To start with the first part, we had said that a distributed system gives a single system image which has no shared memory, and all the processes within the system are going to be sent or interacting with each other by passing messages among machines. So when a message is transmitted from one machine to the other machine, so that the processes from one location can execute with the other location, there may be some transmission delays. And to understand the transmission delay and to avoid it and to ensure that things happen at the same time, we will look at the theoretical foundation, which is fundamental to the concept of distributed computing. Now let's see a distributed system. In a distributed system, we have got individual machines which are distributed across locations, and they are interconnected through a network. We understand that each of these machines will have its own clock, but there is no global clock in the system. So all these machines are going to interact and work at their own time. And when we talk about a message sent by one machine to the other, I can have a timestamp added to it. For example, when you open up your machine and you are starting to work with the machine, you'll find that there's a small clock which is playing, which is timing out on your machine. So that clock is the time which you have, and it may not be the same as the clock which is in your watch, or may not be the same as the wall clock in your house. So different clocks across different machines in a distributed system are going to have different time intervals. So it is required that when systems are interacting with each other, all of them should have a common clock. That is one. So we have one single clock which every machine can see, which is theoretically good to say, but practically difficult to achieve. Or we can use synchronized clock at all machines. That means at equal intervals of time, we need to ensure that every system is going to synchronize and all the clocks will always have a single time. Both these approaches look good, but they can create a problem, because when we talk about a common clock for all machines, wherever be the clock, you have to get the time from there, and the time required may be different. So the message delay may ensure that now the clock time which you have may not be accurate as the clock time which was actually in the clock. Suppose we were to use synchronized clocks everywhere, it is possible that some of the machines the clock may drift And if the drift rate is going to be different, all the clocks will not have the same time. So these are some of the inherent limitations of a distributed system. Absence of a global clock. Take a very simple example. If we talk about a metro like Mumbai, we have got various local trains which travel in different directions. Assuming I have a train which starts from Churchgate and goes up to Virar, and there are say 20-25 stations on the way. Now imagine the clock at every station. If the clocks are not synchronized and if all of them are going to operate at different timings, how will we ensure that the time period taken from one station to the other will be exactly the same as the time which is shown on station 1 and on station 2? So in such a system, it is important that the railways implement a single clock at every place, which is theoretically good to say but practically not possible, or synchronize all the clocks every interval of time. For example, every 1 hour, every station is going to ask the main clock at Churchgate, what is the time right now, and then accordingly synchronize. It's possible that exactly at a particular interval of time, say 12:00, they may not make a call. So again the small time period will be different. So these small intervals of time can create havoc in a system where transactions are involved. So hence in a distributed system, having a global clock is important, and somehow we have to have all the machines interacting together so that they use a single clock in place. Since a physical clock is not possible, we may need to have various algorithms which can enable a system to manage the time and synchronize together. So this was about the global clock. There is one more important aspect of the global time. Because the time available is across the system is not present as a single value, there may be message delays. Even a message delay is not going to allow synchronization of the physical clock. And whenever we talk about an event, whenever an event is occurring, we need to order the event in such a way that if event A happens, then event B will happen, then event C will happen. And the time periods of each have to be in increasing order. If there is any small issue in the system, if the ordering is not exactly the same, then there will be a problem in ensuring the temporal ordering of events. Take a very simple example of operating system scheduling. On a single machine, when you have various processes and they have to be executed on the CPU, and the operating system wants to carry out scheduling, what will happen? To carry out this particular scheduling, all the processes will be put into a queue, and based on some algorithm like round robin or maybe FIFO, processes will be brought out from the queue and the CPU will execute them for a short interval of time and then put it back in the queue, and this will go on. It's good in a single system, but when I talk about a distributed system and have got a scheduler which has to schedule all the processes from all the machines, from all the users, so that they execute on every machine, and we have to ensure that the scheduling happens properly. Timing has to be taken care of, and instant of time is important. It's not just saying 12:00, it's also up to minutes and also up to seconds. So that exact time is important. So for example, when I talk about operating system scheduling in case of distributed system, absence of a global clock does not allow us to carry out temporal ordering of events. Means ordering of events in terms of time. Say event 1, then event 2, then event 3. This temporal ordering is important. Also, it is difficult to design and debug an algorithm which is going to be used for scheduling, because in a system we use different types of scheduling algorithms. As I told you earlier, we may have FIFO, we may have other algorithms, like round robin in terms of small quantum of time or larger quantum of time. Also, another important point is, suppose at a particular moment of time, if we want to know which of the machines are free and where some processes can be executed, I want to know the state of the system. For that, I need an instant at which the state is going to be seen. So if I want to find out the system status at any moment of time, it has to be in terms of time. And the last part over here is, distributed scheduling is a little difficult to implement, because at any moment of time, you have to keep on managing all the machines. We have to find out which ones are free and where particular processes can be executed. And then when the processes have completed the operations, they have to be brought back. Sometimes processes may have to be consolidated together. So the results have to be consolidated, and then the output has to be given to the user. So operating system scheduling in a distributed environment is more complex and is going to become more and more difficult to do just because global clock is not present in the system. The other inherent limitation of a distributed system is that all the machines are individually connected to each other. They don't have a single RAM memory. Each one of them has got individual memories. There is no shared memory existing among them. So when a particular user or the middleware or the distributed operating system is going to look at this particular system, you can get a coherent partial view of the system, or you can get a complete incoherent view of the system. What exactly coherent means? Different processes are going to keep on executing at the same time. So when different processes are executing, I need to know what is executing where. So that idea has to be taken. The second part is, in a distributed environment, the middleware or the operating system needs to have complete view of local views on every machine and collect them together and to then look at the global state of the system. Because a clock is not present, because the shared memory is not present, it becomes a little difficult to understand how to get the global state or how to get the complete view of the system. Now, let's take a very simple example to understand what happens when there is no global clock or where there is no shared memory in a distributed system. Take an example of a particular database which is distributed on two sites, site A and site B. On site A, we have an account in a local bank, so the entire system is a banking database. In this particular bank, the local account, the balance is around 500 rupees. You have another account in another location where the balance is 200 rupees. And suppose now you have user A with a balance of 500 who wants to send 50 rupees or credit 50 rupees into an account B, which is another location. Now when this credit has to be done, see what would happen. Once the operation is complete, 500 reduces to 450 while 200 is going to become 250. But this 50 information is going to transfer or go as a message from A to B, which is in two different locations. It is not on the same database. That's where the problem occurs. If it was on the same database, it is very quick and you wouldn't even know how much time it would take to finish this operation. But when the locations are different, the message of 50 rupees credit is going to travel over the network, and it depends on the network how much time will be required to transfer the 50 rupees from one location to the other location, from one account into the other account. Now, while these particular operations are going on, it is possible for me to collect the global state of the system such that 500 has become 450, 50 rupees has come out from here, but the 50 rupees message has not reached here. So when I collect the information from here, if the clocks were not correct, then the information I get from this particular machine would be 200 and not 250, which is wrong. So 50 rupees is hanging out in between and nobody knows, because here there is 450, but here there is no credit of 50. That's a problem in the system. There is another problem, that if the clocks were not correct and if one of the clocks is moving very fast and I collect the global state from both of the machines, this has sent for 50 rupees, it has come here, but 500 change has not been made and 200 here becomes 250. Again 50 rupees is hanging in between because you find extra 50 in the system. So such incorrectness in the system is going to exist because there is no global clock and there is no shared memory. To look at it like this, if both these operations were to happen in a single shared memory, so 500 becomes 450 and 200 becomes 250. The credit and the debit happen parallelly, then there is no problem. But unfortunately in a distributed system, we do not have a single shared memory, we don't have a single clock. So when I am going to collect the global state, I know that I am collecting it from here, I am collecting the exact balance from here, but both of them may not be at the same instant. If the instants are different, it is possible, like in the earlier case I told you, 500 has become 450 and 50 rupees is not traceable, or 500 remains as it is, debit actually has not happened, and on the other side we have a credit of 50. Both these things are problems. To avoid these issues in distributed environments, we need to have some algorithms in place, and those are the concepts in theoretical foundations. So in the next topic now, let's start with the topic of clock synchronization. But before that, let's see what a computer clock is. Every computer has got a small quartz crystal which is going to keep on oscillating at a particular frequency. As the crystal keeps on oscillating, we have a counter register which will keep a track of the oscillations. And as a particular value, say oscillations happen up to 60, 1 minute incrementing happens. When oscillations happen such that 1 minute becomes 60, you have 1 hour increments. So accordingly, the electronic time can be noted with the help of quartz crystals on a single computer. Now, depending on whatever different operations which have to be done internal to the processor and to the other systems on the motherboard, the same clock is used. Either it is divided in terms of multiple values and used across the system. So the basic oscillation of a second is what we call as a clock tick, and a clock tick is an interrupt which is generated, and every time a clock tick happens, the counter is going to be incremented. So when the counter value reaches 60, we can say that 1 minute has occurred. We assume that when 60 ticks happen, 1 second will be done, or maybe 1 minute will be done. Now that tick period is important. If the tick period changes slightly, then 1 minute may actually come out to be 1 minute and 5 seconds, or it may also be 53 or 55 seconds, which could be a problem. So the tick is very important because exact time period of 1 second is important to note. So computer clocks are basically synchronized with real time. Now if you look at your watch on your laptop, for example my laptop right now is showing me say a time of 10:30, means what? Right now quartz crystal was oscillating and I was getting some values. Now that is mapped with real time, and so I can say right now that the time in my watch is 10:31 AM. So when we say computer clock and we synchronize the computer clock, we talk in terms of a fixed starting time and the date, and we also talk about the number of ticks. So clock synchronization basically is based on quartz crystals and the oscillations of the quartz crystals. Now the point here is that as the quartz crystal is going to be used over a period of time, it's going to age, and as it is going to age, it will start having that 1 second period which may vary slightly. If it keeps on slowly elongating, the actual 1 second time is going to change and it will impact on 1 minute and hours. That means we can say that the clock is going to drift. And to relate it to a very live examples, let's look at, you have a wristwatch with you and you have a battery in the wristwatch. Initially when you take a new battery and you put in your watch, the watch works very well. You are able to show the time which is perfect as per the time which you had set it down. Maybe after 3-4 months you find that the battery is going to age. The clock may start slowing down. It's not stop working, but it slows down. Means the battery, the time at which it was showing earlier is now elongated, and 1 minute happens a little longer. It takes a little longer time to complete a minute. That's where the problem is. So when the clock is going to drift, it's going to make the time go slow. This clock drifting also happens on a computer. Hence, we say that adjusting the laptop once and or a computer machine once and say that the clock is going to work well is not right, because after some time, depending on the age of the quartz crystal, the clock is going to drift. And we need to understand that if there is a drift, it is going to hamper the actual real time in the network. It's also possible that sometimes the clock is going to be fast or the clock is going to be slow. And in both the cases, the difference is going to be there, whether it is positive or negative. And that positive negative difference cannot be tolerated because the drift is going to change the actual time in the circuit. So due to slight difference in the oscillation frequency, there may be a small drift in the time period, and the drift value is typically called as dc by dt. Ideally it should be 1, but if it is a fast clock, the time will be very fast and the drift rate is going to be higher. So now when we talk about the drift in the clocks, we have got a term which is used called as clock skew. The clock skew is the difference between two clocks of two different machines. That means if I have one clock, say for example you have a wristwatch and one of your friends also has a wristwatch and both of you check your times. It's not possible that both of them will always have exactly the same time. So maybe my watch right now is showing 10:35 and maybe his watch is going to show 10:38 or maybe 10:32. So that small difference is called as clock skew. Now the other term used in clocks is called as clock drift. And as I told you earlier, when computer is going to count at different rates, the oscillations may be either fast or they may be slow. And over a period of time, the clock value which was supposed to be 1 will either be little more or it could be little less. So we cannot say that I have adjusted the time today and it's going to work for lifetime. So after some time, there may be a small drift and I have to now bring it back to the actual value. And this is exactly what you do with your physical watches. And typically what happens, wrist watches don't go drift very fast. But if you look at your wall clocks, you'll find that the battery, since it's larger in size, the battery doesn't last much. And so very often you find that after some time the clock is going to go slow. So you have to go and adjust it, and again it will run for some days. After some days again it may go slow, again you'll have to go and adjust it. So you are adjusting your clock because there is a drift. You are adjusting your clock with the real time. The other part in this particular concept of the wall clock which I told you, you try to see the clock time and you see your time in the wristwatch. The two are different. And then you say, okay, there is a skew and I don't like a skew, I want both of them to work at the same time. So you go and adjust your watch. So there is a clock skew, there is a drift, and so you want to adjust it with real time. In terms of computers, we have got a standard time controller which is called as UTC, Universal Controller for Time. Is a particular controller which is an atomic oscillator which is keeping on vibrating or oscillating at a particular speed which is fixed across the world. Now it is not a quartz oscillator, it is an atomic oscillator. The main function of this oscillator is to keep on broadcasting the time to everyone around, and it is also activated through the GPS. So any particular machine across the world will be able to match with the UTC time and calculates its own time and adjusts its own time. That's how the physical clock is adjusted. Now this concept which I talked about of clock in terms of computers, in terms of your wristwatch, or in terms of the wall clock, this is a physical clock because it's the actual time which is shown. Now take another very simple example where you understand the impact of having physical clock which is drifting with time. Suppose you have a particular machine where you have made a file, and this file is suppose made at a particular time interval, say 10:52. And now this particular file is made and it is to be compiled and it is sent over to another machine. Now if that machine was running slowly or if that machine was running fast, then you wrote it here but you cannot compile it before. So if this other machine was running very slow by say 15 minutes, you code the file at 10:52, but you cannot recompile it or compile it at say 10:30. So that's something weird. So in this particular example, you can see that when you make a file here, unless you make a particular file, you cannot run it or compile it. So the event here has to happen before this event, and the time period here has to be less than the time period for compiling the file. So in such cases, you cannot have a particular clock on this machine running slower than this machine. And this is where the concept of logical clocks came in. So physical clocks exist in a distributed environment, but for some processes, we can use the concept of logical clock. And what does the concept of logical clock say? It says that you have a particular event happening here. Say the time is x. X plus something will be the event which happens up here because it happens afterwards. So we don't want to know whether it is 10:20 or 10:21 or 9:50 or say 4:45 in the evening. I just have to know time x, and this time has to be more than this because it happens afterwards. So that's where the concept of logical clock talks about. There are few algorithms for physical clocks and logical clocks which we will see one by one. Now the first thing we'll look at is a term which is called as clock skew. Clock skew is basically the difference in the values of the two clocks. Whenever the two clocks are going to be synchronized, skew has to be very small or has to nearly go to 0. This is one concept. The second important point is, whenever events occur in a particular system, event and time cannot go backwards. Means if you have one operation happening here and this operation or a process has to execute after that, time over here cannot be later than time here because the event has happened afterwards. This is the second part. So it is important that whenever we talk about a clock, if there is a drift in the clock, faster clocks have to be slowed down and slow clocks have to be fastened up to ensure that all of them are working at the same speed in a distributed environment. So to manage the time in the entire system, we use algorithms for physical clocks, which can be centralized algorithm and distributed algorithm. In centralized algorithm, it is something like this, that in the example of the station which I took, I said that we have about 25 stations from Churchgate to Virar, that is one of the Western Railway local trains in Mumbai. Now in this particular system, suppose assuming there are 25 total stations, I will have one controller station. If it is a centralized algorithm, the control is at one single place which is going to monitor and inform everyone the time in the circuit. And all the clocks at all the stations are going to manage that particular time and change that time. If it is a distributed system, then every station on the way is responsible for changing his own clock. That's how the difference is between centralized and distributed systems. So let's look at the two algorithms in centralized algorithms for synchronizing the clocks. The first one is called as a time server algorithm. I have one machine which runs a process which is called as a time server. The function of the time server process is to inform everyone the actual time in the circuit. So this particular centralized algorithm can be divided into passive algorithm and active algorithm. Now as you are already aware, passive means I keep quiet and somebody else is going to send me the message. Active algorithm, I have to send a message. And this is exactly what happens in passive time server algorithm and the active time server algorithm. In the passive time server algorithm, each node or each machine is going to send a message and ask, what is the time right now? The machine is going to send everyone, the time server is going to send a message to everyone and say, time now is T. Now see what happens. This particular transmission of sending the request for the time and giving back the reply is traveling over the network. It's going to take some time. And it depends on where the machine is located in the network. Maybe if a distributed system is across different locations, the one machine is here while the time server is here, so it will have to travel and come back. So what the client does, when the client gets that particular time, it will also incorporate 2 times the travel time and average it out. Because suppose if we say 1 second was required to go and 1 second was required to come back, according to that particular time, this time value here which was received will be incremented and incorporated. So this correction is done by the person himself or by the machine himself. Now machine means what? Actually the algorithm. So this particular algorithm consists of 2 parts, one part running on the server, that is the time server, and the other part of this particular algorithm running on each client machine. Now all these client machines are going to run this algorithm at periodic intervals of time to ensure that their clocks don't drift. And at periodic intervals of time, they are going to initiate a process, send a message for what is the time and get a reply back and then do the correction. This is passive time server algorithm because the calculations are done not by the time server but by the individual machines. Now comes another algorithm. Now when each of them does it, some of them may be very accurate in doing it, some of them may miss out some time. It is possible that time calculations may not have been done very accurately. So the other way of doing is we use an algorithm called as active time server algorithm. In this particular algorithm, instead of everyone sending the messages, because so many messages are transferred over the network is going to become congested, create problems in the system, and other messages will not get space to flow. So to avoid this, the active time server algorithm says that why ask everyone to send? I'll only send the message to everyone. So every periodic interval of time, the time server is going to check its own time, calculate it with UTC, calculate the correct value at this instant and send it off to all the machines. All the machines will pick up that time, check their own time and accordingly calculate the drift of delta for the message to travel from the server to the machine, incorporate it and do the correction. So after this correction is done, the actual time will be stored by each of the machines. This will continue. After some time, again the active time server will send the message, again the calculations will be done. So over a period of time, periodic calculations ensure that the drift is reduced and all the systems are working at the same interval of time. And this actually makes the system easier to synchronize with each other. Yeah, so this particular algorithms which we talked about are also called as Christian's algorithms, where we talked about the time server which is going to manipulate the time by calculating it with UTC and then sending off to everyone as a request and a reply message. Then after these algorithms, we have one more point over here, that while these systems are working well, what if one of the machines is not working correctly and the time is not calculated correctly? It is possible. If it is going ahead of time is okay, but if by chance, if the clock is very slow, it is possible that event happening here, when it reaches here, the time here will be less than this, which actually could create a problem in the system. So time is going to run backwards, which cannot be allowed in the system, and this care has to be taken by the entire system. Also, another problem with these two algorithms is timing. We have to know the exact time delay between the machine and the server and back, and that depends on which path is being taken. If the path is long, the time may be different, so the actual time calculation also could be different. So these are some of the minor problems where delay may not be accurately taken and the time which is calculated right now for the machine may not be accurate. But this is very small problem. It's not that there's going to be a large drift. There will be a large skew in the system. But in centralized algorithm, the main problem is single point of failure. If server is going to fail, then all the systems will be waiting and they will not be able to calculate the time. Hence, in most of the systems today, as systems are small, centralized algorithms are preferred, but as the system expands, we need to have distributed algorithms in place. So there was an algorithm which was called as the Berkeley algorithm. Yeah, so in this Berkeley algorithm, what we have is a time server which is going to poll every machine and ask what is the time right now. So as I told you in the example earlier, I need to have all watches in my house synchronized with one time, while my neighbor's house can have all the watches synchronized with a different time or with the same time, but both of them need not be equal because groups are different. The people who are going to interact with each other are different, so there can be two different times. So instead of going to UTC and asking for the time, Berkeley algorithm says that don't have a centralized server, because if there's a single point of failure, the entire system will go down. So instead of that, we ask the time server to send a message to everyone, and poll, ask everyone, what's the time right now, get this all times together, calculate the average, add the difference of the delays, because every message which is going to come from the machine will have some small delay. So take an average delay, incorporate the delay, and then send this actual time to all the machines. Now when every machine gets this particular time, it will again add the difference and calculate the actual time. So this is how the algorithm can take care in terms of master and slaves, and all of them can average it out and get the particular time. But again here, there is a small problem. If the master fails, the system may go down. Immediately once the master fails, another machine is elected as the master. That particular master will initiate the process and start carrying out the time, and these calculations can be carried out. Now the other point over here is, look at it like this, that it's very easy to ask 10, 20, 30 machines to ask for the time. 30 messages will be coming in. But if there are 100 machines, 100 messages will actually clog the network and it will lead to a large traffic in the network. Now time is not an important process in the system. Other processes also going on, because computers in the system are interacting to carry out their own processes. Yeah, so in the Berkeley algorithm, this particular server process which is going to run is actually called as a time daemon. A time daemon is a background process which is going to run on every system to calculate the time and wait for the time server process to ask for the time and poll for the time, and accordingly the calculations are carried out. Now this particular algorithm, how it works is shown in the figure, where we have the time daemon which is calculating the time as 300, and it's going to poll and ask the two machines what is the time right now. The two machines are going to send the time. One of them says it is 2:50, and the other one says it is 3:25. See the difference. Like this, it is not just two machines, but the system may have many machines and all of them will start giving the actual time which they have on their clocks. Now when these times are brought in, Over the network also some time will be spent. So for example, the 250 actually takes 10 units to come in. That time is calculated. The 325 takes about 25 units to come and travel and come to the time server. So both these calculations are taken into account. Now instead of bringing the actual time, we just get the delta. So the first case which I told you earlier, we send the actual time. All the machines are going to send the time and the average will be calculated. In the second case, a little modification of the algorithm is the time server is going to send the time to everyone and say, okay, this is the time right now. You don't send me your time, you just send me the difference. So when this 3 value is sent to all the machines are going to send back the difference of the time, whether it is plus or minus. Now these plus or minus values are all incorporated on the time server, they are averaged out. And then this average value is calculated. It could either be plus or minus, and this single value is sent back to all the machines. All the machines will add or subtract that value and calculate the current value and start working with that clock. That's how the Berkeley algorithm would work. So in the first case, as I told you, it was asking everyone, and the second case not asking everyone but sending the current time and asking for the delta. Now what is the advantage in the second part? When you ask for the delta, you are just asking for the difference. So it is easier to send and manage instead of asking for the actual time in the system. So with these centralized systems, we look at another algorithm. Actually, we will try to reduce the network traffic, which is the distributed algorithm. In distributed algorithm, the responsibility for managing the time is with the single individual machines and not with the time server. We will also use a server, or we may also ask everyone to ask each other what is the time and synchronize them together. So when we want to synchronize the clocks, we are going to use real time. So internal synchronization is done in terms of real time for all the clocks together. So the first distributed synchronization is called as global averaging distributed algorithm. In this particular algorithm, every node or every machine is going to broadcast a particular time, and it is called as a resync message. Now this particular time is sent to everyone, and each machine is going to send the time. So every machine will get, say if there are 10 nodes, every machine will get 10 messages coming in. It will average out the time and it will adjust its time accordingly. So the botheration of managing each time is periodically done by individual machines by asking all the other machines to send them the time. Now the problem here is there is a lot of traffic, because every node is sending a message to every other node for the current time and asking them for their time. So in the distributed algorithms, we will look at two different algorithms, global averaging distributed algorithm, and the other one is called as localized averaging distributed algorithm. What do we do in the global average distributed algorithm? It is a distributed algorithm. That means all the nodes are responsible for managing the time. It's an averaging algorithm. So all the times are received and they are averaged together, and it is global, means every node is going to manage its own time. So how does this particular global averaging distributed algorithm works? Clock on each node is going to wait for a particular time and collect resync messages from all the other nodes, and this will be done by every node. When the messages are going to come in, it will calculate a small skew with respect to the other node. So I have my time, but I may receive somebody else's time, as say I have got a time of 10:20, but somebody else sends me 10:25 and the other one sends me 9:30. So skews are taken, skews are averaged out, and after that averaging it out, my actual time is calculated. Now the part over here is, it is possible that some clocks may be very slow or some clocks may be very fast. So what's the point in taking those? So in the global averaging distributed algorithm, so all the skews are taken and we follow what is called as a bell curve. In the bell curve, we don't look at the extremes, we just pick the in between values where the skews are predominant. So the large skews and the lower extreme skews on both the sides are left out, and only the averages are taken in between, and accordingly the average can be calculated. So the remaining skews are discarded to compute this particular average. This actually evens out the procedure. In the other algorithm, which is called as local averaging distributed algorithm, the skew is calculated over logically arranged grid pattern of the local network. So instead of traveling over the entire network, I divide this distributed system into small subnetworks. Now this is required because the distances are very large. What is the point in calculating time here where in this particular system where these machines are very far away? Why do I bring them, why do I send the messages here? Because that's going to travel over the network, it will increase network traffic, it will slow down other system performance, and it will also increase the number of messages which will come to this machine. So the entire distributed system is divided into local subnetworks, and the averaging of the time is done within each subnet separately, and this actually is good for large systems. So this is how distributed algorithms are going to work. So after looking at the various algorithms for clock synchronization for physical clock, that is global and localized algorithms, centralized and distributed, we will now look at another important concept which is called as logical clocks. To understand the concept of logical clocks, let us first look at what is a happened before relationship. When we talk about a global clock, we say that a distributed system does not have a global clock. So how do we understand that happened before relation will take place? What exactly is this? A happened before relation means when one event occurs and after that a second event has to occur, then the time of the second event should be more than the time of the first event. This is called as a happened before relationship. It also means that time cannot go backwards. So for example, we say that every processor or every node has got its own local physical clock. Now the local physical clock actually is going to be incorporated as a timestamp. So in the happened before relationship, we talk about a global clock where we talk about the clocks, and we say that whenever a particular process is running on a particular system and it sends a message to another system and it initiates a process on the second system, the clock on the second system will always have a value more than the earlier one. And whenever we send the messages, we also attach a timestamp to it to ensure that the second clock machine with the clock will have an increased time. So this basically we talk in terms of a counter for a logical clock, and we say that a happened before relationship is denoted by an arrow which is defined as, if we say that A happens before B, then A and B are events in the same process where A has occurred before B. And we also say that if A is an event of sending a message M in one process and B is the event of receiving this particular message on another process, then A happened before B. Also we can say that when A happened before B and B happened before C, then A also happened before C, because obviously the clocks are going to be different for each. So this was basically the main concept of happened before relationship, which has enabled us to modify. Instead of talking about just physical clocks, we will talk about logical clocks. Also, another important concept in happened before relationship and event ordering is like this. If two events are not related by the happened before relationship, then they can be concurrent. We can also have something called as happened before relationship is also called as causal ordering, because one of them is impacting the other one. Say for example, I go to the ATM machine and I take a balance statement. It's okay. It's just one operation which I have done. But if I make a credit or if I make a debit and then I take a balance, the balance process which I do, which is initiated now, is dependent on the first process of debit. So they are causally related to each other. So from this particular concept of happened before relationship, we move into the concept of logical clocks, and we say that whenever a particular event is occurring, let us attach a timestamp to it. And we say that whenever a particular process A is executing on a system, it has got a clock say C, and when this particular process completes and it sends a message to another process, maybe on the same machine or on another machine, and we say that A happened before B, clock of A will always be less than clock of B. Now here we are not talking about the real time, we are just saying a numerical value of the clock, whether it is a real time or otherwise, the numerical value is less than the second one. Thank you.